Okay, so let's just talk about these limits. A couple of people had questions. So you're just really talking about end behavior still. We're still just talking about end behavior. It's just a new notation. So if you want to talk about the left end behavior, you're talking about x approaching, x going left is x going in the negative direction. So you write it as the limit as x approaches negative infinity of the function equals, and then you just state the end behavior. So this, when you're reading this notation, when you see a negative x approaching negative infinity, you should just be thinking going to the left, right? As this function goes to the left, the end behavior continues to infinity, up forever, so up to infinity. The limit from the right, in other words, as x is going this direction, as x is going to positive infinity, the limit of this particular function is going down, so it approaches negative. So it's going to negative infinity. End behavior down. Does that make sense? Anybody still have questions on that one? Okay, so this one, this last one, end behavior, right? This end behavior, the limit as x approaches negative infinity, so that's to the left. What's that? Where is that going? End behavior, negative infinity. I'm getting cut off here. Negative infinity. And what about from the right? Limit as x approaches infinity. This is actually approaching 1. You see, that would be called an asymptote. It's approaching 1, but it's never going to actually cross 1. That's an asymptote, which we'll deal with later. Okay, so our goal here is to be able to graph functions that have, you know, different degrees, etc., by interpreting the equation and knowing what the equation's telling us. So really our goal is two things: to be able to graph them, or to be able to read a graph and know what the equation's going to look like. All right? So with that in mind, knowing our goal here, there's a couple of patterns and, you know, characteristics that we want to notice that relate an equation to its graph. So first of all, the leading, they call it the leading term test here, but you're looking at that first term, right? Your first term is written like this: a sub n, right? This is the first term of x to the n. This is your first term. Where a sub n is the coefficient, that's the number part of it, right? And x is your variable, and then to the n is going to be the degree. N is the degree. Okay, so we talked about this a little bit already, but if n is even, in other words, if the first term has a degree that's even, right, that first power is even, then the end behavior is going to resemble a parabola, right? Because the parabola is the x squared, that's the even function that we're most familiar with. So it's good to kind of relate it to that one because that's what we're used to. So we know that a parabola goes like that if the coefficient is positive. And we know that a parabola goes like this if the coefficient is negative. It's like an upside down U, right? Now, obviously, that's a degree of 2. We're generalizing the end behavior only, right? A degree of 4 is not going to graph like a parabola, but the end behavior is going to be the same. That make sense? So notice this one, up and up, just like the parabola goes up and up, etc. Okay? There's a little jig-jag in here, so clearly it's not a parabola, but the end behavior is the same. And this is the way we write end behavior, just like we were talking about above. Okay, if n is odd, so the end behavior resembles an S shape. Like I said, I like to think of it as resembling a line, a linear graph. Because the line, y equals mx plus b, right, is a degree of 1, so that's odd. It's an odd degree polynomial. So the end behavior of all odd degree polynomials is going to match that. This S shape is referring to this kind of thing. Okay, so if it's positive, again, if you think of a line with a positive slope, it goes from left to right, down to up. It goes up in the increasing direction. If it's negative, it's in the decreasing direction. It goes from up to down. So end behavior of all odd functions are going to match that same end behavior pattern. Any questions on that? All good? Okay. All right. The degree, like we talked about, is your highest exponent. It's the number of possible real zeros, also called roots, also called solutions, also called x-intercepts. Right? Some could be double roots, meaning if you have a equation that looks like this, when it's x plus 1 and it's squared, meaning there's 2 of those roots, right? That's multiplicity. There's like more than one. That's a double root. So this refers to how that impacts the graph, and this is what Cameron was talking about before. If there's an odd number of factors, so here, right, there's 2 of these factors, so that's an even number of factors because it's 2 of them. And this is an odd number of factors because it's only to the first power, right? That's odd. So when we have an example of a function like this, we know just by that factored form that when it's an even number of factors, it's just going to touch the x-axis, not go through it. So this particular example that I just randomly came up with, at x equals -1, there's an even number of those factors. We know it's just going to touch, not go through, right? And at x equals 2, it's going to have an odd number of factors, right? So it's going to cross. It's going to actually go through like this. Actually, I should have gone the other way. Yep, messing you up already. But I should have touched this way and then gone through like that. How do I know that? How do I know that I had it backwards? It's positive, so my end behavior has to match the positive, right? What is the degree of this random function that I just came up with? Be careful. What is it? It's actually 3, right? Because this is x. This x gets squared eventually, And then there's another x. So when we multiplied this all out, we would end up with an x to the third, right? Okay, so vice versa here, if we start with a graph, we can tell what these zeros are going to do. So here's another example, right? This is x minus 1 to the third power. So at x equals 1, positive 1, we know we have a 0. And it's an odd number of factors, so it's just going to cross. It's going to go through at 1. Here we have x equals negative 2 as one of the zeros. And it has an even number of factors, right? Because it's to the fourth power. So it's just going to bounce off of it. So it's really a bounce versus a cross through, okay? Okay, so when we're graphing these functions, these are some things to think about, right? You want to look at the leading term, right? The leading coefficient. That number in front. Is it negative or is it positive? That's going to be an effect on your graph because that affects your end behavior. I'm going to call that an L for leading, right? Leading term. So the end behavior is affected by the coefficient, whether it's positive or negative. But it's also affected by the degree. That's my D, degree. Odd or even also affects the end behavior, right? So positive, negative, and odd or even. There's really two things to consider in that leading term. So I have my L for the leading coefficient and my D for the degree, but it all comes from that first term. Okay? The next thing you want to do is factor. That's my F. Thus, the let's do functions. Right? That's just to help you remember to do those three things. Look at the leading coefficient for odd for positive or negative. Look at the degree for odd or even, and then factor it. Or look at the factored form to help you to see where the zeros are, etc. Okay? Okay, so in this first example, k minus 1 to the third power, x plus 2 to the fourth power. This is an odd. This is an even. So that's the factored form. But let's think back to the leading coefficient. The first term. If this is to the third and this is to the fourth, what is the degree of this whole polynomial? 7. And is the leading coefficient odd or even? I'm sorry, is the leading coefficient positive or negative? Leading coefficient. Do we have any negatives? No, this is going to be positive. So we know it's positive and it's odd, and that affects our end behavior. And then the multiplicity can be told by these factored form and whether it crosses or touches. Okay, we're out of time.